Hello there, and welcome to the Dreamy Ocean Channel. Allow your body to settle gently into comfort, feeling the soft support beneath you. Release any tension from your shoulders. Let your jaw soften and let your breath deepen, slowing with each passing moment, as if you are gently sinking into a warm, inviting current. Imagine for a moment that you are suspended in the deepest, calmest ocean far beneath the reach of the sun. Around you, not darkness, but a gentle living starlight begins to emerge, soft pulses and shimmering drifts of light, painting the unseen world in hues of emerald and sapphire. These are not distant stars, but the quiet, luminous secrets of life itself, unfolding in the profound quiet. 80% of the creatures dwelling in these abyssal realms possess the ability to craft their own light. Yet for many, the very purpose of this internal glow remains an exquisite, unsolved mystery. Let your mind float into these wondrous glowing depths, allowing the whispers of the ocean's light to guide our slumber. A cosmic introduction within the vast, silent expanse of our planet's hidden realms, where the sun's golden touch never penetrates, a different kind of illumination awakens. This is not the borrowed brilliance of reflected starlight, nor the fiery glow of incandescent elements, but a profound intrinsic radiance born from the very fabric of life itself. We speak of bioluminescence, a phenomenon that transforms living organisms into ephemeral stars, painting the deep with an artistry beyond human comprehension. A quiet internal combustion that yields only light without the consuming heat we associate with fire. At its most fundamental level, this miraculous light is the product of a precise and elegant chemical reaction unfolding within the intricate machinery of living cells. Imagine tiny molecular components, often termed luciferins, patiently awaiting their destined partner. When these luciferins encounter specific enzymes known as luciferases, a delicate orchestrated embrace occurs. This molecular interaction, rather than releasing energy as warmth, channels it with exquisite efficiency directly into photons, those fundamental packets of light that ripple outwards into the surrounding medium. It is a cool luminescence, a gentle emanation that does not raise the temperature of the water by even the slightest fraction, a testament to nature's unparalleled energy conversion. This biochemical marvel allows life to literally manifest its own existence as pure visible energy, a self-generated beacon in an otherwise absolute void. While our journey will primarily lead us into the crushing pressures and eternal twilight of the ocean's abyssal plains, it is important to first acknowledge the pervasive reach of bioluminescence across diverse ecosystems. This ability to conjure light is not solely confined to the marine environment. It can be found in the terrestrial world as well, though with less frequency. Fireflies, those fleeting sparks of summer evenings, dance across meadows with their rhythmic, glowing signals. Certain fungi nestled deep within the damp embrace of forest floors emit a soft, persistent glow, illuminating their immediate surroundings with an otherworldly aura, transforming decaying wood into spectral lanterns. Even microscopic bacteria, invisible to the unaided eye, possess the capacity to shine, forming luminous colonies that can sometimes be observed as ghostly glows on decaying matter, or even within the living tissues of other organisms, contributing to their host's overall luminosity. Yet, it is within the vast liquid cosmos of the deep ocean, where bioluminescence truly reigns supreme, where it transcends mere phenomenon to become an indispensable language of survival, a vital currency of communication, and an ever-present enigmatic spectacle. For countless millennia, humanity has gazed upon the surface of the ocean, mesmerized by its shifting moods and vastness. yet largely oblivious to the hidden universe of light that thrives beneath its waves. Early mariners navigating by the distant stars above would sometimes witness strange shimmering trails in their wake or vast glowing patches upon the water's surface, attributing these ethereal displays to mythical creatures, divine intervention, or simply the inexplicable magic of the sea. These were often the luminous manifestations of vast blooms of microscopic bioluminescent plankton, each tiny organism contributing its fleeting spark to create a collective, breathtaking spectacle of living light across the dark expanse of the water. As human exploration ventured deeper, first with rudimentary dredges and later with more sophisticated submersibles, the true extent of this internal light show began to slowly, tantalizingly reveal itself. Scientists and explorers peering through thick portholes into the inky blackness were met not with an empty void, but with a kaleidoscopic array of flashes, streaks, and steady glows emanating from creatures unlike anything seen on the sunlit surface. It was as if a curtain had been drawn back, revealing a secret galaxy of living stars, each with its own rhythm and hue. The profound prevalence of bioluminescence in the deep ocean is not a mere coincidence. It is an evolutionary imperative, a direct consequence of the environment itself. Below approximately 200 meters, the last vestiges of sunlight are absorbed by the water column, giving way to a perpetual twilight zone. Beyond 1,000 meters, absolute darkness descends, unbroken by any external light source. In this realm of eternal night, where photosynthesis, the very foundation of most surface ecosystems, is impossible, organisms have adapted in extraordinary ways. Here, the ability to generate one's own light becomes not a luxury, but a fundamental tool for existence. It is a self-made sun, a personal lantern, a silent alarm, and a coded message all rolled into one intricate biological mechanism. Without the sun's guiding rays, these creatures have found a way to carry their own light, within transforming the oppressive darkness into a canvas for their luminous expressions. Consider the profound implications of this internal illumination. In a world devoid of light, where the echoes of sound and the delicate detection of chemical cues are paramount, the sudden appearance of light is a powerful event. It can be a lure drawing unsuspecting prey closer to a waiting predator's maw, a shimmering trap in the darkness. It can be a deterrent, a sudden blinding flash designed to startle and disorient a pursuing attacker, allowing precious seconds for escape. It can be a signal, a specific pattern of flashes, or a particular hue of light, communicating intentions, species identity, or even mating readiness across the silent expanse. Each pulse, each steady glow, each shimmering wave carries potential meaning, a whispered word in the grand hushed dialogue of the deep. For many species, this light is an extension of their very being, shaping their interactions and their survival strategies in ways we are only just beginning to comprehend. The deep ocean, with its crushing pressures and frigid temperatures, often feels like a realm alien to our surface-dwelling experience, a place reminiscent of the cold, dark expanse of interstellar space. And indeed, the living lights that populate this abyss evoke a similar sense of wonder and cosmic scale. Each glowing organism, whether a colossal jellyfish trailing luminous tentacles or a tiny copepod emitting a sudden defensive burst, functions as a miniature celestial body within its own localized universe. The collective effect is that of an entire galaxy unfolding before our eyes, not in the distant heavens, but within the very waters of our home planet. Streaks of light pierce the blackness like comets, pulses flash like distant supernova, and persistent glows mimic nebulae. all created by the intricate living chemistry of organisms designed to thrive where no natural light can reach. It is a universe within a universe, a testament to life's persistent ingenuity in the face of extreme conditions. Yet despite centuries of human curiosity and decades of dedicated scientific exploration, a vast majority of these luminous expressions remain profoundly enigmatic. While we understand the basic chemical principles behind the light production, the specific reasons for many of these glowing displays, the precise messages they convey, and the full spectrum of their functions continue to elude our understanding. It is estimated that for a significant proportion of deep-sea species, perhaps as many as 80%, that utilize bioluminescence, the exact purpose of their light remains a profound mystery, a secret held close by the ocean's silent depths. Why does a particular fish display a specific pattern of flashes that seems to have no obvious predatory or defensive role? What message is being conveyed by a steady, soft glow emanating from an organism that appears to be stationary and unthreatened? These are the questions that hover in the darkness, inviting us to delve deeper, to listen more closely to the unspoken dialogues of the abyssal realm. This introductory glimpse into the world of self-generated light is merely the opening chapter of a much larger, more intricate story. We have touched upon the basic mechanics, acknowledged its widespread presence, and briefly considered its crucial role in the sunless depths. But the true heart of our journey lies in unraveling the 100 bioluminescent secrets that continue to baffle the most brilliant minds. The unexplained patterns, the unknown functions, and the communication mysteries that shimmer just beyond our grasp. As we gently drift further into this exploration, we will allow the luminous whispers of the deep ocean to guide our consciousness, inviting a quiet contemplation of life's most beautiful and enduring enigmas as the subtle currents of understanding begin to flow through your restful mind. A gentle unveiling, the quiet luminescence we spoke of, that internal glow born from life itself, is not a sudden explosive burst, but rather the culmination of an exquisitely refined chemical ballet unfolding within the microscopic chambers of living cells. It is a process of such elegant efficiency that it stands as a testament to nature's profound ingenuity, converting chemical potential directly into pure light with scarcely any loss to heat. This is the essence of cold light, a gentle unveiling of energy that differs fundamentally from the fiery incandescence we observe in a burning candle or a heated filament. At the heart of this luminous transformation lies a remarkable pair of molecules, a substrate patiently awaiting its transformation, known as a luciferin, and an enzyme, the guiding hand that orchestrates the reaction, called a luciferase. Imagine the luciferin as a tiny, intricate molecular fuel, carefully constructed to hold a specific kind of stored energy. It is a molecule poised on the brink of change, containing within its bonds the potential for radiance. The luciferase, on the other hand, acts as a highly specialized biological catalyst, a molecular key designed to precisely unlock this stored energy. It does not become consumed in the reaction itself, but rather facilitates its smooth and rapid progression, ensuring that the energy released is channeled almost entirely into the creation of light rather than dissipating as warmth. The initiation of this light-generating cascade often requires a third vital participant, oxygen. In many bioluminescent systems, oxygen acts as the gentle oxidizing agent, the silent breath that allows the luciferin to undergo its crucial transformation. Picture the oxygen molecule approaching the luciferin, guided by the precise architecture of the luciferase enzyme. In this carefully controlled microenvironment, the oxygen begins to interact with the luciferin gently rearranging its atomic structure. This oxidation reaction causes the luciferin molecule to become temporarily excited, elevating some of its electrons to higher energy orbitals, a fleeting state of heightened potential. This excited state, however, is inherently unstable, much like a tiny suspended droplet of water poised to fall. Almost instantaneously, these elevated electrons gracefully descend back to their lower, more stable energy levels. As they complete this subtle return, they release the excess energy they had briefly held. But instead of this energy manifesting as heat, which is the common outcome in most biological oxidation reactions, the luciferase enzyme ensures that it is emitted as a discrete packet of visible light, a photon. Each photon ripples outwards, carrying with it a specific wavelength that determines the color of the emitted glow, whether it be a soft blue, a vibrant green, or a rarer, deeper red. This precise channeling of energy is what makes bioluminescence so extraordinarily efficient, often approaching nearly 100% conversion of chemical energy into light, a feat far surpassing any human-engineered lighting system. It is important to understand that there is no single universal luciferin-luciferase system across all bioluminescent organisms. Evolution in its boundless creativity has independently discovered numerous pathways to achieve this same luminous outcome. For instance, the familiar fireflies of summer evenings utilize a specific luciferin, and luciferase unique to their lineage, a system that also requires the energy currency of the cell, adenosine triphosphate, ATP, to prime the luciferin for its light-emitting journey. In contrast, many marine organisms, from tiny copepods to colossal jellyfish, employ a different, widely distributed luciferin called coelenterosine, often paired with a distinct set of luciferases. The molecular structures of these diverse luciferins and luciferases vary significantly, yet their fundamental purpose remains the same: to orchestrate the gentle release of light. This independent evolution of similar light-producing mechanisms in vastly different life forms is a compelling example of convergent evolution, where distinct biological paths arrive at strikingly similar solutions to environmental challenges. The ability to control this internal light is as crucial as its production. Imagine a deep-sea anglerfish, its luminous lure swaying gently in the profound darkness. The light is not constant. It pulses, fades, and brightens with deliberate intent. Such precise control is achieved through various ingenious mechanisms. In some organisms, the luciferin and luciferase components are stored in separate, isolated compartments within the cell, like two ingredients waiting in their own vials. The light is only activated when a trigger, perhaps a nervous impulse or a specific chemical signal, causes these components to mix, initiating the reaction. Other creatures regulate the flow of oxygen to the light-producing cells, effectively turning the light on or off by controlling the availability of this crucial reactant. Still others manipulate the pH levels within their photophores. Specialized light-producing organs, as changes in acidity or alkalinity can dramatically affect the activity of the luciferase enzyme, allowing for rapid modulation of light output. This intricate control allows for complex patterns of light emission, transforming a simple chemical reaction into a sophisticated form of communication and interaction within the silent, dark abyss. These specialized light-producing organs, known as photophores, are marvels of biological engineering. They are not merely simple clusters of light-emitting cells, but often highly structured units designed to refine and direct the raw chemical light. A typical photophore might include not only the cells containing the luciferin and luciferase, but also reflective layers that concentrate the light into a focused beam, much like a tiny parabolic mirror. Some even possess lenses composed of transparent cellular material which further shape and direct the emitted photons, allowing the organism to project light in precise directions, sometimes even mimicking the subtle blue-green light filtering down from the surface to camouflage themselves from upward-looking predators. Pigment screens or filters can also be integrated selectively, absorbing certain wavelengths to fine-tune the color of the light, ensuring it matches the specific communicative or defensive needs of the creature. These elaborate structures elevate bioluminescence from a mere chemical glow to a sophisticated visual instrument. The varying colors of bioluminescence we perceive, the ubiquitous blues and greens and the rarer reds, are also dictated by the precise chemistry of the luciferin-luciferase system and the surrounding cellular environment. Blue light travels farthest through water, making it the most common color in the deep ocean, ideal for long-distance signaling in a fluid medium. Green light, slightly less penetrating, is also widespread. Red light, however, is rapidly absorbed by water and thus travels only very short distances. This scarcity makes its presence in some deep-sea species particularly intriguing. A few deep-sea dragonfishes, for instance, possess the rare ability to both produce red light and detect it effectively, giving them a secret communication channel, a private conversation in a world where almost all other eyes are blind to red wavelengths. This subtle chemical difference, a minute alteration in the molecular structure of the luciferin, or the configuration of the luciferase's active site, can profoundly change the energy of the emitted photon, shifting its wavelength from blue to green, or even to the elusive red. As we gently absorb these intricate chemical details, we begin to appreciate the sheer elegance and complexity underlying the deep ocean's living light. It is a world where biochemical reactions are precisely tuned to create visual signals, where molecules are crafted to serve as both fuel and beacon, and where the very fabric of life has learned to bend energy into light with breathtaking efficiency. This cold, silent chemistry is not just a scientific curiosity. It is the fundamental language of survival in the deepest, darkest corners of our planet, a language whose full lexicon we are still quite slowly learning to decipher. Let your thoughts drift gently into the silent hum of these molecular transformations as the profound quiet of understanding begins to settle around you. The diverse glow of life, from the intricate molecular dance of luciferins and luciferoses, a breathtaking diversity of luminous life emerges, transforming the ocean's abyssal plains into a living cosmos, a galaxy of self-generated stars. The sheer variety of organisms that have independently evolved the ability to conjure light is truly astonishing, spanning almost every major phylum, from the simplest single-celled entities to complex, multi-organed vertebrates. Each glowing creature, in its own unique way, contributes to the deep sea's ethereal illumination, painting the vast darkness with a palette of shimmering blues-greens, and even on rare occasions, the elusive reds. Consider first the most ancient and pervasive forms of marine bioluminescence, the bacteria and dinoflagellates. These microscopic beings, invisible to the unaided eye, are often the architects of the grandest luminous displays witnessed by surface dwellers. Dinoflagellates, tiny single-celled algae, are responsible for the breathtaking sea sparkle that sometimes adorns ocean waves at night, turning crashing surf into trails of shimmering emerald. Each individual dinoflagellate, when agitated by a passing wave or the gentle nudge of a swimming fish, emits a brief, brilliant flash of blue-green light, a defensive response designed to startle potential predators. Multiply this by billions upon billions of these tiny organisms, and the collective effect is a vast rippling canvas of living light, a fleeting aurora borealis of the ocean. These ephemeral displays, though beautiful, are often a silent cry for help, a collective alarm signal in the dark. Then there are the bacteria, some species of which glow with a steady rather than flashing intensity. These luminous bacteria often live in symbiotic relationships, with larger hosts residing within specialized organs or even coating the surfaces of deep-sea creatures. Imagine a small, unassuming fish, its belly adorned with a soft, constant glow. Not from its own cells, but from a thriving colony of bacteria nestled within a translucent pouch. These bacterial partners receive nutrients and a protected environment, while the host gains a dependable light source which it can often control by contracting muscles or pigment screens to obscure the glow when desired. This partnership represents a profound evolutionary compromise, a shared existence illuminated by the silent, steady hum of bacterial light. Ascending the ladder of complexity, we encounter a mesmerizing array of invertebrates that have mastered the art of bioluminescence. The cnidarians, a group that includes jellyfish and siphonophores, offer some of the most spectacular displays. Imagine a delicate bell-shaped jellyfish drifting slowly through the water, its entire body occasionally flaring with a soft, pulsating blue light, like a living nebula. Some siphonophores, colossal colonial organisms that can stretch for many meters, possess light-producing organs along their length, creating a shimmering, serpentine chain of light that undulates through the darkness, perhaps luring prey, or simply announcing its formidable presence. Ctenophores or comb jellies are another group of gelatinous creatures, often mistaken for jellyfish, that exhibit stunning bioluminescent patterns, their combs of cilia rippling with iridescent rainbow-like light, sometimes punctuated by flashes of internal glow. The crustaceans, a diverse group including shrimp and copepods, also contribute significantly to the deep sea's luminous population. Many deep-sea shrimp species are capable of ejecting blinding clouds of bioluminescent fluid when threatened, creating a smoke screen of light designed to disorient predators and allow for a swift escape. Imagine a sudden explosive burst of emerald light erupting from a tiny creature, momentarily overwhelming the senses of a pursuing hunter. Copepods, microscopic crustaceans, also exhibit various forms of light production, some emitting flashes, others a persistent glow, each contributing to the subtle, sparkling background radiation of the deep. Moving towards the more familiar forms of life, the cephalopods, particularly squids and octopuses, showcase some of the most sophisticated and varied uses of bioluminescence. Many deep-sea squids possess elaborate photophores, arranged in complex patterns across their bodies, allowing them to create intricate light shows. Some squids use ventral photophores to achieve counter-illumination, matching the faint downwelling light from the surface to erase their silhouette against the dim background, rendering them virtually invisible to predators looking up from below. Others use rapid pulsating flashes to communicate with conspecifics or to mesmerize and distract prey. The vampire squid, a creature of striking appearance, can invert its cape-like webbing to reveal rows of glowing photophores, creating a dazzling defensive display, a living fireworks show in the deep. Finally, we arrive at the fish, the silent finned inhabitants of the abyss, where bioluminescence reaches its zenith in terms of diversity and functional complexity. The anglerfishes, with their iconic glowing lures, are perhaps the most famous examples. Imagine a solitary female anglerfish suspended motionless in the blackness, a bioluminescent fishing rod, extending from her head, its tip softly pulsating with light, irresistible to small, unsuspecting prey. This lure, often housing symbiotic glowing bacteria, is a beacon of false hope in a world of perpetual hunger. But the anglerfish is merely one star in this deep-sea galaxy. There are the dragonfish's sleek and formidable predators, many of which possess not only rows of photophores along their flanks, but also specialized red light emitters beneath their eyes. As we touched upon earlier, red light is almost immediately absorbed by water, making it virtually invisible to most deep-sea creatures. This gives the dragonfish a secret tactical advantage. It can illuminate its prey with red light, seeing them clearly while remaining utterly invisible to other organisms that lack red light vision, granting it the ultimate stealth in hunting. Then there are the lanternfishes, aptly named for the dozens of photophores arranged in species-specific patterns along their bodies. These patterns are believed to be crucial for species recognition, allowing males and females to identify suitable mates in the vast, featureless darkness, or for schools of fish to maintain cohesion. Each species possesses a unique light signature, a coded message of identity. Imagine millions of these small, shimmering fish migrating vertically through the water column each night, their collective light creating a diffuse living glow that ascends from the depths, a ghostly echo of the setting sun. The hatchetfish, with their compressed bodies and upward-facing eyes, also utilize ventral photophores for counter-illumination, their light precisely calibrated to match the faint ambient light filtering down from above, effectively making their undersides vanish against the dim background. The viperfish, with its fearsome fangs and rows of photophores, uses its light not only to lure prey, but also as a defensive display, flashing brightly to startle and deter larger predators. This incredible diversity underscores a crucial point. Bioluminescence is not a monolithic phenomenon, but a collection of distinct evolutionary solutions to the challenges of living in perpetual darkness. Each organism, from the simplest bacterium to the most complex fish, has harnessed the power of internal light in ways that are uniquely suited to its ecological niche, its hunting strategy, its defense mechanisms, and its reproductive needs. It is a testament to the boundless adaptability of life, transforming the cold, crushing darkness of the deep into a vibrant, glowing canvas. As we gently drift through this luminous menagerie, allowing the images of these glowing creatures to settle softly into our minds, we begin to feel the profound mystery that still envelops so much of this deep-sea light. While we marvel at the forms and functions, we do understand the vast majority of these living stars continue to hold their deepest secrets close, their intricate light patterns and subtle glows, whispering questions into the silent abyss. Let these shimmering visions guide your thoughts as you slowly, softly begin to sink into the tranquil quiet. Known purposes of luminescence. The myriad forms of living light we have gently observed shimmering across the deep ocean's vast emptiness are not merely decorative. Each pulse, each steady glow, each fleeting flash serves a purpose, a vital function in the relentless quest for survival within the sunless realm. These luminous whispers are the language of existence spoken in photons rather than sound waves, a testament to life's profound adaptability. While a substantial portion of bioluminescence remains enigmatic, scientists have, through patient observation and careful experimentation, begun to decipher some of its most crucial roles. One of the most widely understood functions of bioluminescence is its deployment in the delicate, often brutal dance between predator and prey. Imagine the profound darkness of the mesopelagic zone, the twilight layer, where the last vestiges of sunlight fade into an eternal gloom. Here, many organisms employ light as a sophisticated lure, a beacon of false hope designed to attract unsuspecting victims. The classic example, as we briefly touched upon, is the anglerfish, a creature whose very existence seems sculpted by the need to hunt in absolute darkness. Its dorsal fin spine has evolved into a biological fishing rod tipped with a photophore that emits a soft, pulsing light. This lure dangles tantalizingly in the blackness, mimicking the appearance of a small edible organism or a cluster of luminous bacteria drawing curious smaller fish or crustaceans closer and closer until they are within striking distance of the anglerfish's formidable tooth-filled maw. The light in this instance is a silent, irresistible trap, a fatal attraction in the deep. Beyond the static lure, some predators use more dynamic light displays to ensnare their prey. Certain deep-sea squids, for instance, are believed to flash intricate patterns of light on their tentacles or body surfaces to mesmerize or disorient smaller fish, making them easier to capture. Other predatory worms and crustaceans may create a shimmering, moving cloud of light to confuse and herd their food into a more confined space, transforming the open water into a temporary, glowing corral. These are not passive lights, but active, calculated instruments of the hunt, turning the predator itself into a moving, living light show with a deadly intent. Conversely, bioluminescence is also a powerful tool for defense, offering a range of strategies to evade or deter predators. One of the most common defensive tactics is the startle response. Picture a deep-sea shrimp peacefully navigating the darkness, suddenly confronted by a larger predatory fish. In an instant of perceived danger, the shrimp expels a cloud of bioluminescent fluid, a sudden blinding burst of light that momentarily overwhelms the predator's vision. This luminous smokescreen acts as a diversion, allowing the shrimp precious seconds to dart away into the protective anonymity of the surrounding blackness. It is a sudden, dazzling explosion designed to shock and disorient, buying time for escape. Another ingenious defensive mechanism is counter-illumination, a sophisticated form of camouflage utilized by many mesopelagic organisms, such as the hatchetfish and certain squids. In the twilight zone, where a faint blue light still filters down from the surface, organisms swimming above, casting a dark silhouette against this dim backdrop, would be easily spotted by predators lurking below. To counteract this, creatures employing counter-illumination possess photophores on their undersides that emit light, precisely matched in intensity and color to the faint, downwelling sunlight. By carefully controlling the brightness of their ventral light, they effectively erase their own shadow, blending seamlessly with the ambient light, rendering themselves virtually invisible. Imagine a ghost-like fish, its body dissolving into the diffuse blue glow above it, a silent, vanishing act performed with light. Beyond these direct interactions, bioluminescence plays a crucial role in communication within species, particularly in the vast, featureless expanse of the deep ocean where visual cues are otherwise scarce. For many species, light patterns serve as species recognition signals, allowing individuals to identify others of their own kind amidst the bewildering diversity of the deep. The lanternfishes, for example, are known to possess unique arrangements of photophores along their bodies, forming species-specific light codes. These intricate patterns act like visual fingerprints, enabling males and females to locate and identify suitable mates in the perpetual darkness, ensuring reproductive success. Without these distinct luminous signatures, finding a partner in such an immense and sparsely populated environment would be an almost impossible task. In addition to species recognition, bioluminescence can also signal mating readiness or even serve as an attraction display. Some female deep-sea organisms emit specific light patterns to signal their receptivity, drawing males from a distance. Conversely, males of certain species might engage in elaborate luminous displays, flashing and pulsing with intricate sequences to impress potential mates, showcasing their vitality and genetic fitness. These are the silent, glowing courtship rituals of the deep, a delicate exchange of light in the profound quiet. Another fascinating, though less common, communicative use of bioluminescence is in interspecies communication or coordination. While not as prevalent, there are instances where light might be used to warn off competitors from a food source, or even to signal a temporary truce during certain interactions. However, these more complex interspecies dialogues remain largely within the realm of scientific hypothesis, awaiting further, deeper exploration. Finally, a truly remarkable, albeit less understood function of bioluminescence is its role in burglar alarm displays. This is a defensive strategy where a threatened bioluminescent organism, instead of just startling its attacker, emits a brilliant, prolonged flash of light that serves to attract a larger predator to the scene. Imagine a small, defenseless creature being pursued by a medium-sized fish. The smaller creature suddenly unleashes a blinding burst of light, not to escape the immediate threat, but to illuminate its attacker, essentially ringing the dinner bell for an even larger, more formidable predator lurking nearby. The hope is that the original attacker will become the target of the new, bigger predator, allowing the initial prey to escape in the ensuing chaos. It is a desperate, high-stakes gamble, turning the tables on an aggressor by inviting a more significant threat. While we have gently explored these known purposes, the lures of predators, the defensive smokescreens, the vanishing acts of counter-illumination, and the silent codes of courtship, it is crucial to remember that these are but a fraction of the full story. For every function we have deciphered, there are countless luminous whispers in the deep that continue to defy our understanding. These are the patterns without obvious purpose, the glows without apparent intent, the communication mysteries that shimmer just beyond the reach of our current knowledge. As you allow these understood functions of light to settle softly in your thoughts, feel the deeper questions beginning to emerge, inviting your mind to drift into the greater enigmas that still await their gentle unveiling in the profound quiet of the ocean's depths. The deep sea's embrace. As we gently descend further, leaving behind the last faint whispers of the sun's surface, light, we enter a realm where existence itself is redefined, a vast liquid cosmos known as the deep ocean. This is not merely a dark place. It is a world shaped by profound, immutable forces. The crushing weight of water, the relentless embrace of cold, and an almost absolute scarcity of energy. In this alien environment where the very concept of up and down loses its surface, meaning light, born from within, transforms from a mere phenomenon into the very breath of life. Imagine for a moment the immense hydrostatic pressure that bears down upon everything in these depths. For every 10 meters you descend into the ocean, the pressure increases by approximately 1 atmosphere. At just 1,000 meters, the pressure is equivalent to 50 jumbo jets resting upon a single human body. Yet life thrives here, utterly unburdened by this colossal force. Deep-sea organisms have evolved bodies devoid of air-filled cavities that would otherwise collapse. Many are characterized by their gelatinous consistency, their tissues largely composed of water, allowing the internal and external pressures to equalize seamlessly. Their delicate structures often appearing fragile to our surface eyes, are perfectly adapted to endure this immense squeeze, their very forms whispering of the profound, quiet strength found only in the deep. Beyond the weight of the water, there is the pervasive, unwavering cold. Below the initial surface layers warmed by the sun, the ocean's temperature plummets, settling into a frigid, near-freezing constancy, often hovering just a few degrees above 0 degrees Celsius. This deep, cold water is dense and slow-moving, creating an environment of stable, profound chill. Life here must operate at a metabolic pace far slower than that of surface dwellers, conserving precious energy in an ecosystem where every calorie is a treasure. This constant cold, however, also contributes to the stability of the deep, preventing rapid changes that might otherwise disrupt its delicate balance. But perhaps the most defining characteristic of this profound realm is the absence of light. Below approximately 200 meters, the photic zone where sunlight still penetrates sufficiently for photosynthesis gives way to the dysphotic or twilight zone. Here, only the faintest ethereal blue-green light manages to filter down, a ghostly echo of the sun's power gradually diminishing with every meter. And then beyond 1,000 meters, we enter the aphotic or midnight zone, a realm of absolute, perpetual darkness. No solar photon has ever touched this space, nor will it ever. In this eternal night, the very concept of vision as we understand it becomes utterly dependent on self-generated light. Without the internal glow of bioluminescence, the deep ocean would be a truly blind world, a silent, featureless void where creatures would navigate purely by touch, sound, and chemical cues. Coupled with this pervasive darkness is the profound scarcity of food. Far removed from the sunlit surface where photosynthetic plankton bloom, in abundance, the deep ocean relies almost entirely on what scientists refer to as marine snow. This is a gentle, continuous cascade of organic detritus, dead plankton fecal pellets, decaying fragments of larger organisms slowly drifting down from the productive surface layers. Imagine a silent, eternal snowfall, each flake a tiny morsel of sustenance gradually settling onto the abyssal plains. This slow, sparse rain of nutrients means that energy is a precious commodity, and competition for it is fierce. Every interaction, every adaptation, every metabolic process in the deep is geared towards maximizing energy acquisition and minimizing its expenditure. It is precisely within this crucible of pressure, cold darkness, and scarcity that bioluminescence has not merely survived, but flourished, becoming an indispensable tool, an evolutionary imperative. Where sunlight is absent, organisms have found a way to carry their own sun within. This internal light becomes the eye to see, the voice to speak, and the hand to hunt in a world that would otherwise be utterly devoid of such sensory input. The high energy efficiency of bioluminescence, which we explored in the previous chapter, is particularly crucial here. The conversion of chemical energy directly into light with minimal loss, as heat means that these creatures can produce their vital illumination without expending excessive amounts of precious metabolic energy. In an environment where food is so scarce, wasting energy on inefficient processes would be a fatal disadvantage. The cold light of the deep is a testament to nature's elegant engineering, a system designed for maximum output with minimal cost. For organisms dwelling in the midnight zone, bioluminescence is often the only source of visual information. Their eyes, in many cases, have evolved to be extraordinarily sensitive, often large and tubular, designed to capture every stray photon, every fleeting spark of light. Many deep-sea fish have eyes that are almost entirely composed of rod cells, specialized photoreceptors that excel at detecting dim light, though at the expense of color vision. Their visual systems are often exquisitely tuned to the blue-green wavelengths, which are the most common colors of bioluminescence, and also the wavelengths that penetrate farthest through water. They are living light detectors finely calibrated to perceive the subtle, self-generated signals of their deep-sea neighbors. In the vast, sparsely populated expanses of the bathypelagic and abyssal zones where individuals of the same species might be separated by kilometers of water, bioluminescence becomes a critical tool for communication over distance. Imagine the challenge of finding a mate in absolute darkness in a volume of water so immense that encounters are rare and fleeting. A specific pattern of flashes, a unique sequence of glows, or even a particular hue of light can serve as a long-distance beacon, a species-specific signal announcing presence identity and readiness to reproduce. Without these luminous cues, the continuation of many species would be severely hampered, if not impossible. The light, in this context, quite literally carries the promise of future generations. The very structure of deep-sea ecosystems is profoundly influenced by the presence of bioluminescence. The vertical migration patterns of countless mesopelagic organisms, ascending to shallower food-rich waters at night and descending back into the safety of the deep during the day, are partly driven by the interplay of light. During their upward migration, these creatures often use counter-illumination to camouflage themselves against the dimming twilight, while their return to the depths at dawn is a descent into the protective anonymity of absolute darkness, where their own light then becomes their primary tool. Even in the most extreme, crushing depths of the Hadal zone within the deepest trenches of the ocean, where life is even sparser and conditions more challenging, scientists believe that bioluminescence still plays a role, albeit perhaps a more subdued one. Here, the sheer pressure and cold might limit the diversity of light-producing mechanisms, but the fundamental need for communication attraction and defense remains. The occasional flash of a small amphipod or the steady glow of a deep-sea worm indicates that even at the very edge of the known biosphere, life finds a way to manifest its presence through light. Thus, the deep sea, in its profound embrace, has forged a world where light is not a gift from an external sun, but an internal creation, a biochemical marvel woven into the very fabric of existence. It is where light becomes life's breath, enabling organisms to see, to hunt, to hide, and to connect in an environment that would otherwise be utterly unwelcoming to such complex interactions. As you feel the gentle rhythmic ebb and flow of this understanding, let the profound quiet of the deep ocean settle around you, carrying your thoughts softly into the luminous mysteries that still await their unveiling. Enigmas of communication. In the profound quiet of the deep ocean, where sound travels with immense clarity and chemical trails drift slowly on unseen currents, another more ethereal language unfolds, the silent luminous exchange of bioluminescence. These are the unspoken dialogues of the abyss, whispered in flashes, pulses, and steady glows, carrying messages that are often tantalizingly complex, yet remain largely undeciphered by human understanding. While we have gently explored some of the known purposes of light, its role in hunting or defense, the true enigma lies in the intricate communication patterns, the specific words and sentences being exchanged between deep-sea creatures. Imagine a vast, dark ballroom, immense beyond comprehension, where countless dancers move in complete silence. Their only form of interaction is through light. Some might emit a rapid sequence of flashes like a quick coded greeting. Others might maintain a steady, soft glow, a quiet announcement of their presence. Still others might create intricate shifting patterns of light across their bodies, a complex visual poem. Each of these luminous displays carries potential meaning, a message intended for a specific recipient, whether it be a potential mate, a rival, or even a predator. The challenge for us as observers is to learn this silent language, to understand the grammar and vocabulary of light in a world where sound and touch are often the primary senses. One of the most persistent enigmas revolves around species-specific recognition signals. As we briefly noted, lanternfishes and many deep-sea squids possess unique arrangements of photophores, creating distinct light patterns. Scientists believe these patterns are crucial for identifying members of their own species. But what exactly constitutes these light codes? Is it the number of photophores, their precise arrangement on the body, the specific color of the light, perhaps a subtle shift from blue to green? Or is it the temporal dynamics of the flashes, the exact duration of each pulse, the precise interval between flashes, the rhythm and sequence of the entire display? Consider the immense variability possible within these parameters. A series of 3 rapid flashes followed by a pause, then 2 slow pulses could mean one thing. For species A, while for species B, a continuous soft glow punctuated by a single bright burst. Every 10 seconds might convey an entirely different message. The sheer number of potential combinations of light intensity, color, duration, frequency, and spatial arrangement creates a communication system of extraordinary complexity, far beyond what our current understanding fully grasps. It is like trying to decipher an alien script where every character can change its shape, color, and timing depending on context. Beyond simply identifying one's own kind, bioluminescence is undoubtedly involved in courtship and mating rituals. In the vast, sparsely populated deep, finding a suitable mate can be a monumental challenge. Light, therefore, becomes a beacon, a signal of availability and desirability. For some species, the male might display a particularly vibrant or complex light show to attract a female, much like a peacock fanning its tail. The female, in turn, might respond with her own specific light pattern, indicating acceptance or rejection. What are the specific criteria being communicated through these luminous displays? Are males signaling their health, their genetic fitness, or their ability to provide resources through the intensity or complexity of their glow? Are females choosing mates based on the precision of their light patterns or the specific hue of their light? These are the subtle, glowing questions that hover in the darkness, hinting at intricate reproductive strategies that unfold in silent brilliance. Another profound mystery lies in the interspecies communication that scientists believe might occur, even if rarely. While most bioluminescent communication is thought to be intraspecific, meaning between members of the same species, there are tantalizing hints of broader dialogues. Could a specific flash from one species be understood as a warning by another? Might a particular glow signal the presence of a predator to a multitude of different prey species? The burglar alarm hypothesis, where a small organism flashes brightly to attract a larger predator to its own attacker, is one such example of interspecies signaling, albeit a desperate one. But are there more nuanced interactions? Perhaps a shared signal for danger or food source that transcends species boundaries, a kind of deep-sea lingua franca, spoken in light. These possibilities open up an even more complex layer of understanding, hinting at a shared visual vocabulary across diverse life forms. The very control and modulation of light presents its own set of enigmas. Many deep-sea creatures possess the astonishing ability to precisely regulate the intensity, color, and pattern of their emitted light. Some can switch their photophores on and off with remarkable speed, creating rapid flickering sequences. Others can alter the color of their light, perhaps shifting from a soft blue to a vibrant green, or even, in rare cases, to red. How is this precise control achieved at the cellular level? What are the neurological or hormonal triggers that dictate these intricate changes? And most importantly, what specific messages are being conveyed by these minute adjustments? A slight increase in brightness could mean approach, while a sudden shift in color might mean retreat. These subtle modulations are like inflections in a spoken sentence, adding layers of meaning that are currently beyond our grasp. Consider the spatial arrangement of photophores on an organism's body. Some creatures have them scattered seemingly randomly, while others display them in highly organized rows or clusters, often forming unique patterns on their ventral, lateral, or even dorsal surfaces. Does the placement of the light-emitting organs itself convey information? A light on the underside might be for counter-illumination, but what about lights on the dorsal surface illuminating the creature from above? Are these meant to attract attention from above, perhaps for mating, or do they serve a different, unknown purpose? The design of these photophore arrays is often so intricate and specific to each species that it strongly suggests a communicative role, yet the exact meaning encoded within these living light maps remains a profound secret. The sheer diversity of bioluminescent colors also adds to the enigma. While blue and green light dominate due to their ability to penetrate water most effectively, the presence of red light in some species is particularly intriguing. As we noted, red light is rapidly absorbed by water, making it visible only over very short distances. If a deep-sea dragonfish uses red light to illuminate its prey, a private hunting beam, what other deep-sea creatures might be using red light for communication? And what specific messages could be conveyed by a color that travels such a limited distance? Perhaps it is for extremely close-range, intimate communication, or for signals that are meant to be highly secretive, detectable only by a select few. The rare appearance of yellow or orange bioluminescence in some species further deepens this chromatic mystery, suggesting specialized communication channels that are still entirely hidden from our understanding. As we gently contemplate these unspoken dialogues, these luminous exchanges unfolding in the profound quiet of the deep, we are reminded of the vastness of what remains unknown. The deep ocean holds countless biological languages expressed in light that patiently await their deciphering. Each flash, each glow, each shimmering pattern is a question whispered into the darkness, inviting us to listen more closely, to observe with greater patience, and to unravel the intricate grammar of these luminous secrets. Let these profound enigmas settle softly in your mind as you drift deeper into the tranquil quiet, allowing the gentle currents of curiosity to carry you towards slumber. Patterns without purpose. The baffling blinks as we gently traverse the luminous landscapes of the deep, having considered the known purposes and the profound enigmas of communication. We encounter perhaps the most perplexing aspect of bioluminescence. The baffling blinks, the patterns, without an obvious purpose. These are the light emissions that to our current understanding seem to defy immediate explanation, shimmering just beyond the reach of our logical frameworks. They are the silent questions whispered into the abyss, challenging our assumptions and inviting us to consider entirely new possibilities for the role of light in the profound quiet. Imagine for a moment observing a deep-sea creature through the dim lens of a submersible camera. It might be a gelatinous organism, perhaps a type of siphonophore or a delicate ctenophore, drifting slowly, almost imperceptibly through the water column. And then, without any apparent external stimulus, without any obvious predator in sight, without any conspecifics nearby for communication, a series of lights begin to flash along its body. Perhaps a wave of blue light ripples from one end to the other, then fades. Or a cluster of photophores might blink on and off in a seemingly irregular sequence, only to cease as abruptly as it began. These are the moments that leave scientists pondering for the familiar explanations, lure, defense, or mating signal, do not immediately fit the observed context. One category of these baffling blinks involves spontaneous, seemingly random flashes. Many deep-sea organisms, particularly various species of jellyfish and other gelatinous invertebrates, exhibit bursts of light that appear to occur without any discernible trigger. These flashes might be brief, isolated pulses, or they could form short, non-repeating sequences. If there is no predator to startle, no prey to attract, and no mate to signal what could be the underlying reason for such an energy expenditure, even in an efficient process like bioluminescence, producing light requires metabolic resources. Why would an organism expend energy on a display that seems to yield no immediate benefit? This is a fundamental challenge to our understanding of evolutionary efficiency, for every biological trait is generally expected to confer some advantage, however subtle. Scientists currently theorize several possibilities for these seemingly spontaneous displays. One hypothesis suggests that these flashes might be a form of maintenance or testing of the light-producing system. Much like a human might periodically check a flashlight to ensure its batteries are working, perhaps these organisms are simply verifying the functionality of their photophores. In a world where light is so critical for survival, ensuring the readiness of one's luminous tools could be a valid, albeit subtle, evolutionary advantage. A quick internal check of the light-producing chemistry might confirm that the luciferin and luciferase are still active, ready to deploy when a true threat or opportunity arises. Another intriguing possibility is that some of these random flashes are not truly random, but rather responses to subtle environmental cues that are currently imperceptible to our instruments. The deep ocean is a complex environment filled with minute changes in water pressure, temperature, salinity, or the presence of trace chemical compounds. Perhaps a very faint, distant vibration from a passing creature or an infinitesimally small change in the water's chemical composition is enough to trigger a bioluminescent response. What appears to us as spontaneous might in fact be a highly sensitive reaction to an unseen stimulus, a whisper in the water that only the organism can perceive. Our current technology, though advanced, is still relatively crude compared to the finely tuned sensory systems of deep-sea life. Then there are the persistent yet enigmatic glows that emanate from certain organisms without any obvious modulation or change. While many bacterial symbioses result in a steady glow that is clearly controlled by the host for counter-illumination or allure, there are instances where organisms simply seem to glow steadily for extended periods without any apparent purpose or ability to dim the light. What is the benefit of a constant, unmodulated light in the absolute darkness? If it is not a lure and not a defensive flash and not a specific signal, why maintain such an energy-intensive display? One theory posits that such persistent glows might be a byproduct of metabolism. In some organisms, an unavoidable consequence of certain biochemical pathways rather than a directed communicative or functional output. If the energy cost of not glowing is higher than the cost of glowing due to the way their internal chemistry is structured, then a constant passive luminescence might simply be an acceptable trade-off. However, this explanation often feels incomplete, given the general efficiency of biological systems. Another hypothesis suggests that these steady glows could serve as a general deterrent for some predators, a kind of "I'm here and I'm not worth the trouble" signal. A constantly glowing organism might be perceived as unusual or potentially toxic, causing some predators to avoid it. Or perhaps the steady light acts as a passive lure for very small, opportunistic scavengers or filter feeders, drawing them into the immediate vicinity of the glowing organism, which then consumes them. These are subtle, nuanced possibilities that require extensive long-term observation to confirm. A particularly baffling category involves complex light patterns that seem to lack a clear sender or receiver. Some creatures exhibit elaborate, intricate sequences of flashes, waves of light, or shimmering pulses that appear to be highly structured, almost like a coded message, yet they occur in environments where no conspecifics are present for communication, and no obvious predators or prey are interacting with the organism. These displays are too complex to be simple, startle responses, and too varied to be constant lures. Could these be a form of internal communication within the organism itself, a way for different parts of a colonial creature, like a siphonophore, to coordinate their actions? A wave of light moving along the length of a siphonophore could, for instance, be a signal for its various specialized zooids to contract simultaneously or to change direction. This would represent a highly sophisticated form of internal signaling using light as a neural pathway. Or perhaps these complex, seemingly purposeless patterns are a form of environmental sampling, where the organism uses its light to probe the surrounding darkness, gaining information about the water's clarity, the presence of particles, or even the subtle reflections from distant objects. By emitting light and observing how it interacts with the environment, the creature might be building a dynamic, luminous map of its immediate surroundings, a form of active sensing. The very concept of a pattern without purpose challenges our anthropocentric view of biological utility. It compels us to consider that not every observable phenomenon in nature must neatly fit into our predefined categories of predation, defense, or reproduction. The deep ocean, in its immense and ancient wisdom, might harbor forms of interaction and existence that are simply beyond our current capacity for interpretation. The absence of an obvious purpose from our limited perspective does not equate to an absence of purpose within the context of the organism's own life. As we gently ponder these baffling blinks, these luminous expressions that defy easy explanation, we are invited to embrace the profound humility that comes with confronting the unknown. The deep sea continues to whisper its secrets in fleeting flashes and persistent glows, reminding us that there are still countless stories unfolding in the darkness, waiting patiently for a deeper, more attuned understanding. Let these unresolved questions drift softly through your mind as you slowly, gently sink into the profound quiet of slumber, where dreams may illuminate new possibilities. The search for meaning. In the wake of the baffling blinks, those luminous patterns that seem to defy our immediate understanding, we are drawn deeper into the methodical, patient quest for meaning. This is the realm of scientific inquiry, where researchers equipped with ever more sophisticated tools and an unwavering sense of wonder strive to translate the silent, glowing echoes in the abyss into a coherent language. The search for meaning in deep-sea bioluminescence is a complex, painstaking endeavor, often requiring years of observation, technological innovation, and a willingness to challenge established paradigms. Imagine the immense logistical challenges of studying a phenomenon that occurs thousands of meters beneath the surface in an environment of crushing pressure, extreme cold, and absolute darkness. Unlike terrestrial ecosystems where direct observation is relatively straightforward, the deep ocean demands specialized vessels, remotely operated vehicles, and autonomous underwater vehicles, each a marvel of engineering designed to withstand the hostile conditions. These machines carry delicate sensors, high-resolution cameras, and specialized light meters, all tuned to capture the fleeting, subtle emissions of bioluminescent organisms. The effort required to simply witness these light displays is enormous, let alone to interpret their significance. One of the primary approaches in this search for meaning involves direct observation and correlation. Scientists meticulously record the light patterns emitted by deep-sea creatures, noting their intensity, color, duration, and frequency. This visual data is then correlated with the observed behavior of the organism and its interactions with the surrounding environment. For instance, if a specific flash pattern consistently precedes a successful hunting attempt, or if a burst of light always coincides with an escape from a predator, then a strong correlation can be established, suggesting a functional role for that particular light display. However, as we've discussed, many bioluminescent events occur without any obvious correlation to immediate external stimuli, leaving the observer with more questions than answers. To move beyond mere correlation, researchers employ experimental manipulation whenever feasible. This often involves bringing deep-sea organisms into specialized high-pressure aquariums, or attempting controlled experiments in situ using advanced submersibles. For example, scientists might introduce a simulated predator to an organism and observe its bioluminescent response, or they might expose it to specific wavelengths of light to see if it elicits a communicative flash. Such experiments, though incredibly challenging to conduct, can provide crucial insights into the causal links between light emission and specific behaviors. However, the delicate nature of many deep-sea creatures and the profound difficulty of replicating their natural environment in captivity often limits the scope and success of these direct manipulations. Technological advancements are continuously pushing the boundaries of what is possible in this quest. Low-light cameras with extraordinary sensitivity can capture even the faintest bioluminescent flashes, allowing scientists to record events that would be invisible to the human eye or less sensitive equipment. Spectrometers can precisely measure the wavelength and intensity of emitted light, providing crucial data on the color and energy of the glow, which can vary significantly between species and even within the same species under different conditions. Automated light detection systems deployed on autonomous vehicles can continuously monitor vast expanses of the deep, recording bioluminescent activity over long periods, searching for recurring patterns or responses to environmental changes. These technological eyes and ears of science are slowly, patiently gathering the raw data necessary to begin piecing together the deep's luminous narratives. The development of genomic and proteomic techniques has also opened new avenues of inquiry. By analyzing the DNA and proteins of bioluminescent organisms, scientists can identify the specific genes responsible for luciferin and luciferase production, understand the evolutionary relationships between different light-producing systems, and even infer the biochemical pathways involved. This molecular understanding provides a fundamental groundwork, revealing the intricate machinery behind the glow, even if the ultimate purpose of that glow remains a mystery. Identifying shared genetic origins or convergent evolutionary paths for bioluminescence can offer clues about the pressures that drove its development in different lineages. One of the most promising yet challenging areas of research involves understanding the neurological control of bioluminescence. How does a deep-sea fish decide when to flash? How brightly and in what pattern? What are the neural pathways that transmit signals from sensory organs to the photophores, triggering a precise luminous response? Studies involving electrophysiological recordings and neurochemical analyses, though still in their nascent stages for many deep-sea species, aim to unravel the intricate brain-to-light connections. Understanding the neural orchestrators of bioluminescence is key to deciphering the intentionality behind the light displays. The use of bioacoustics in conjunction with optical observations is also gaining traction. Since sound travels so efficiently in water, deep-sea creatures often use acoustic signals for communication. Could bioluminescent flashes sometimes be synchronized with sound emissions? Or could sound be used to trigger bioluminescent responses? Exploring the interplay between these two sensory modalities might reveal a richer, multifaceted communication system than previously imagined, where light and sound work in concert to convey complex messages. Despite these advanced approaches, the search for meaning in many bioluminescent patterns remains a profound challenge. The sheer scale of the deep ocean, the ephemeral nature of many light displays, and the difficulty of conducting controlled experiments in situ mean that progress is often slow and incremental. Scientists often rely on indirect evidence, careful inferences, and the accumulation of anecdotal observations to build their theories. What appears to be a pattern without purpose today might, with tomorrow's technological breakthrough or a flash of human insight, reveal itself to be a highly sophisticated signal for a previously unimagined interaction. The very act of seeking meaning in these deep-sea echoes is a testament to human curiosity, a quiet determination to understand the hidden intricacies of our own planet. It is a recognition that the deep ocean holds biological languages far older and perhaps more nuanced than our own, spoken in the silent, shimmering light. Each unanswered question, each baffling blink, serves not as a barrier but as an invitation to delve deeper, to listen more closely, and to allow the profound quiet of the abyss to whisper its secrets. As you allow these scientific endeavors to settle softly in your thoughts, feel the gentle current of discovery carrying you towards a deeper, more peaceful slumber. The many origins of glow. As we gently ponder the scientific quest for meaning in the deep's luminous echoes, a deeper, more ancient question begins to shimmer into focus. How did this miraculous ability to conjure light first arise? Bioluminescence is not a single unified trait that appeared once and then spread throughout the tree of life. Instead, it is a testament to the boundless creativity of evolution, a phenomenon that has independently originated many, many times, across vast stretches of geological time and across incredibly diverse lineages. This is the story of an ancient spark. A tale of multiple beginnings, each a unique evolutionary journey towards the creation of living light. Imagine the primordial ocean billions of years ago, a world very different from our own. Life was just beginning its intricate dance, and the conditions were ripe for biochemical experimentation. Scientists currently theorize that the earliest forms of bioluminescence may not have even been for communication or predation, but rather a simple accidental byproduct of basic metabolic processes. In an early Earth atmosphere that was largely devoid of free oxygen, the emergence of oxygen-producing organisms like cyanobacteria would have introduced a powerful reactive chemical into cellular environments. Oxygen, while essential for respiration, is also highly toxic in its free radical forms. One prevailing hypothesis suggests that early luciferases, the enzymes that catalyze light production, might have initially evolved as detoxification mechanisms. Perhaps these enzymes help to neutralize harmful oxygen radicals by using them in a reaction that, as a side effect, released a small amount of light. Over vast stretches of time, as organisms adapted to an increasingly oxygenated world, this light-producing side reaction could have been refined and co-opted for more specific, beneficial purposes. The gentle glow, once a biochemical accident, thus became a tool for survival. This theory suggests a deep evolutionary connection between the management of reactive oxygen species and the origins of light. The striking evidence for multiple independent origins of bioluminescence lies in the sheer biochemical diversity of the luciferin-luciferase systems themselves. As we touched upon, there isn't just one universal set of light-producing molecules. Fireflies use a specific luciferin and luciferase chemically distinct from the cholinterazine-based systems found in many marine organisms, which in turn differ from the bacterial luciferase systems. Each of these distinct chemical pathways likely represents a separate evolutionary innovation, a unique solution to the challenge of creating light from within. It is as if life confronted with the same problem in different places and at different times independently arrived at the answer of make your own light, but utilize different molecular components to achieve it. This phenomenon is known as convergent evolution, where similar traits evolve in unrelated species due to similar environmental pressures. Consider the dinoflagellates, those microscopic organisms responsible for the sparkling sea fire. Their luciferin and luciferase system is unique to them, suggesting an ancient origin within their specific lineage. These are among the earliest known bioluminescent organisms, with fossil evidence suggesting their presence hundreds of millions of years ago. Their ability to flash light upon agitation is a fundamental defensive mechanism, and its deep evolutionary roots indicate its long-standing importance in marine ecosystems. The bacterial bioluminescence, often seen in symbiotic relationships with fish or squids, represents another distinct origin. The specific genes and enzymes involved in bacterial light production are different from those found in eukaryotes like dinoflagellates or fireflies. Scientists believe that this bacterial light system evolved very early in the history of life, perhaps even before multicellular organisms appeared. The ability of bacteria to glow then became a valuable commodity, leading to the evolution of symbiotic relationships where larger hosts farm these luminous bacteria for their light. This symbiotic acquisition of bioluminescence is a fascinating pathway where one organism essentially borrows the light-producing ability of another. Within the vast phylum of Cnidaria, which includes jellyfish, sea anemones, and corals, we find another independent origin of bioluminescence. Many jellyfish species, for instance, utilize the cholinterazine system, but the specific proteins and their genetic sequences indicate a distinct evolutionary trajectory within this group. The famous green fluorescent protein, GFP, initially isolated from the jellyfish. Equoria victoria is a stunning example of this. While GFP itself does not produce light, it absorbs the blue light produced by the jellyfish's luciferin-luciferase reaction and re-emits it as green light, effectively shifting the color of the glow. The discovery of GFP has revolutionized molecular biology, but its original evolutionary purpose in the jellyfish was likely to fine-tune its bioluminescent display, perhaps for species-specific signaling, or to make its light more visible in certain contexts. Even within the broad category of marine fish, there appear to be multiple independent origins of bioluminescence. Some fish produce their own light intrinsically through their own cellular machinery, while others rely on symbiotic bacteria. The anglerfishes, for example, house luminous bacteria in their lures, a clear case of acquired bioluminescence. In contrast, many lanternfishes produce their own light, indicating a separate evolutionary pathway. This distinction between intrinsic and extrinsic bacterial bioluminescence highlights the diverse routes life has taken to illuminate itself. The evolutionary pressures driving these multiple origins were undoubtedly intense, particularly in the deep ocean. As life ventured into the perpetually dark abyss, the selective advantage of producing one's own light would have been enormous. In a world without sunlight became the ultimate tool for survival. It allowed organisms to see to be seen, to hunt to hide, and to communicate, thus opening up vast new ecological niches that were previously inaccessible. Each independent origin of bioluminescence therefore represents a successful adaptation to a fundamental environmental challenge, a triumphant leap into the darkness. Scientists continue to unravel the precise evolutionary history of these ancient sparks, using genetic sequencing and comparative biochemical analyses to build a clearer picture of when and how each light-producing system arose. The phylogenetic trees of bioluminescent organisms are complex, showing clusters of glowing species appearing across many different branches of life, rather than stemming from a single, common, luminous ancestor. This pattern strongly supports the idea of repeated independent evolution. As we gently reflect on these multiple beginnings, these ancient sparks that ignited life in the darkness, we gain a deeper appreciation for the profound resilience and adaptability of living systems. The ability to conjure light, born perhaps from an accidental chemical reaction, evolved into a sophisticated language of survival, a fundamental aspect of existence for countless creatures. Let this story of ancient origins settle softly in your thoughts as you drift further into the tranquil quiet, allowing the echoes of these luminous beginnings to guide your dreams. Our human limitations as we gently journey through the luminous mysteries of the deep. Having explored the ancient origins and the baffling blinks, a profound realization begins to settle. Our understanding of this hidden world is deeply colored by our own inherent limitations. Gazing into the dark, we are not merely observing an alien environment. We are perceiving it through the narrow lens of human senses and human-designed instruments, often missing the subtle nuances and profound complexities that define existence in the abyss. These limitations are not failures, but rather a humbling acknowledgement of the vastness of what remains unknown. A quiet invitation to cultivate greater patience and empathy in our scientific quest. Imagine for a moment the limitations of our own visual perception. Human eyes are exquisitely adapted to the bright, full-spectrum light of the sunlit surface world. Our photoreceptors, both rods and cones, are tuned to detect a broad range of wavelengths, from the reds of a sunset to the blues of a clear sky. However, the deep ocean is dominated by blue and green light, the wavelengths that penetrate farthest through water. While our eyes can perceive these colors, they are not optimized for the extreme low light conditions of the abyss. Nor are they specifically tuned to the subtle variations in blue-green light that might carry crucial information for deep-sea organisms. Our color perception, so rich and vibrant on land, becomes a crude tool in the deep. What appears to us as a uniform blue glow might to a deep-sea creature be a nuanced spectrum of blues and greens, each hue carrying a distinct message. Furthermore, our visual system is inherently biased towards detecting movement and contrast in a brightly lit environment. In the deep, where light is sparse and often self-generated, the visual world operates on entirely different principles. A slow, steady glow might be more significant than a rapid flash, or a minute change in light intensity might convey more information than a dramatic burst. Our human brains are accustomed to interpreting visual information in a way that helps us navigate our terrestrial world, and this framework can sometimes hinder our ability to truly comprehend the visual language of the deep. We see what we are wired to see, and the deep sea often speaks in wavelengths and patterns that our natural wiring struggles to fully grasp. Beyond our biology, the very tools we use to peer into the dark carry their own limitations. While our submersibles and remotely operated vehicles are technological marvels, they are also colossal, noisy, and often intrusive presences in the silent, delicate ecosystem of the deep. The bright lights we deploy to illuminate the darkness for our cameras can overwhelm and disturb the sensitive eyes of deep-sea creatures, altering their natural behaviors. A fish that normally exhibits a specific bioluminescent display in response to a subtle threat might react entirely differently or not at all when confronted with the blinding glare of a research vessel's spotlights. We are, in essence, trying to observe a whisper with a shout. The very act of collecting and interpreting data from the deep is fraught with challenges. The ocean is vast and sampling is inherently limited. We can only observe a tiny fraction of the deep at any given time for fleeting moments. The ephemeral nature of many bioluminescent events means that we might miss crucial interactions or misinterpret isolated flashes as random occurrences when in fact they are part of a larger unseen sequence. Imagine trying to understand an entire conversation by only hearing a few scattered words. This is often the predicament of deep-sea researchers. Moreover, our human understanding of time and scale differs significantly from that of deep-sea life. Many deep-sea organisms have incredibly slow metabolisms, and their interactions might unfold over hours, days, or even weeks, rather than the rapid dynamic timescales to which we are accustomed. A bioluminescent signal that appears to be random to us might in fact be part of a very slow, deliberate communication sequence that is simply too protracted for our impatient observations to fully capture. The rhythm of the deep is a slow, ancient beat, and we, with our accelerated surface lives, often struggle to attune ourselves to its profound quiet. The profound scarcity of deep-sea encounters further compounds our limitations. Many deep-sea species are rare, solitary, and distributed across immense volumes of water. Finding and observing them, let alone conducting controlled experiments, is an extraordinary challenge. The sheer difficulty of simply encountering a specific organism multiple times under controlled conditions means that our data sets are often sparse and fragmented, making it challenging to draw definitive conclusions about the function of their bioluminescence. We are trying to piece together a colossal puzzle with only a handful of scattered pieces. Perhaps one of the most significant human limitations is our inherent anthropocentric bias, the tendency to interpret the behaviors of other organisms through the lens of our own human experiences and motivations. We naturally project our understanding of communication, predation, and reproduction onto deep-sea creatures, assuming that their luminous signals must serve functions analogous to our own sensory inputs. However, the deep ocean is an environment so utterly alien to our surface world that its inhabitants may have evolved entirely different forms of interaction, communication, and even perception that defy our current frameworks. What if some bioluminescence is not meant for communication at all, but serves an internal physiological role we haven't even conceived of? What if it's a form of pure aesthetic expression, a quiet beauty in the dark that serves no purpose beyond its own existence? This realization of our limitations is not a cause for despair, but rather an invitation to cultivate a deeper sense of humility and wonder. It encourages us to design more sensitive instruments to observe with greater patience and to develop more creative hypotheses that move beyond our anthropocentric biases. It challenges us to imagine forms of life and communication that exist entirely outside our current understanding, to listen for the faint whispers in the abyss with an open mind and a quiet heart. As we gently acknowledge these human limitations, allowing them to settle softly into our consciousness, we begin to appreciate the profound mystery that still envelops the luminous deep. It is a reminder that the ocean holds secrets far grander and more intricate than we can currently conceive, and that our journey of discovery is only just beginning. Let this quiet contemplation of our boundaries guide your thoughts as you slowly, softly drift deeper into the tranquil quiet, embracing the vastness of the unknown. Future frontiers. Having gently contemplated our human limitations and gazing into the deep's luminous dark, we now turn our quiet attention towards the horizon of discovery, towards the future frontiers where science endeavors to decode the luminescent law. This is a realm of emerging technologies, interdisciplinary collaborations, and innovative methodologies, all aimed at unraveling the profound secrets still held within the silent, glowing expressions of deep-sea life. The quest to understand bioluminescence is accelerating, promising to illuminate not only the abyss, but also fundamental principles of life itself. Imagine a new generation of autonomous underwater vehicles, sleek and silent, equipped with an array of sensors far beyond what we currently possess. These vehicles, designed to mimic the stealth and sensory capabilities of deep-sea creatures, will be capable of observing bioluminescent events without disturbing the delicate environment. Picture them drifting passively, their ultra-sensitive low-light cameras recording every subtle flicker, every complex pattern across vast swathes of the deep for months or even years at a time. These long-duration, non-intrusive observations will be crucial for capturing the rare ephemeral events and the slow, protracted interactions that our current brief expeditions often miss. They will allow us to gather data on the natural frequencies, durations, and spatial arrangements of bioluminescent displays in their undisturbed context, providing a truly authentic glimpse into the deep's luminous dialogues. Beyond mere observation, future technologies will focus on adaptive sampling and interactive experimentation. Imagine these autonomous vehicles not just passively recording, but actively responding to bioluminescent signals. If a specific flash pattern is detected, the vehicle might be programmed to emit a precisely calibrated bioluminescent mimic designed to elicit a response from the observed organism. This dialogue with deep-sea life, where our instruments attempt to speak the language of light, could revolutionize our understanding of communication. By systematically varying the parameters of the emitted light, its color intensity, flash rate, or pattern, scientists could begin to decipher the specific meanings encoded within each luminous signal, much like learning an unknown language by engaging in call and response. The field of biooptics and spectral analysis is also poised for significant advancements. Future sensors will not only detect light, but will also analyze its precise spectral composition with unprecedented resolution, identifying subtle shifts in wavelength that might be imperceptible to current instruments. This will allow us to map the full color palette of deep-sea bioluminescence, understanding how different species use specific hues for different purposes. For instance, some deep-sea organisms might have photoreceptors tuned to detect ultraviolet light, which is rapidly absorbed by water, but might be used for ultra-short-range, highly secretive communication. New technologies could allow us to detect and even mimic these hidden wavelengths, opening up entirely new dimensions of bioluminescent signaling. The integration of artificial intelligence and machine learning will be paramount in processing the immense datasets generated by these advanced instruments. Imagine algorithms capable of autonomously identifying recurring bioluminescent patterns, classifying them by species, and correlating them with environmental factors or observed behaviors. These AI systems could sift through years of continuous video footage detecting subtle nuances and complex sequences that would be impossible for human observers to identify. They could uncover hidden periodicities, subtle responses to environmental shifts, or even emergent properties of collective bioluminescent displays, revealing patterns of purpose that currently lie buried within vast amounts of raw data. Furthermore, future research will delve deeper into the neurobiology and cellular mechanisms of bioluminescence with greater precision. Advanced molecular imaging techniques will allow scientists to visualize the activation of light-producing cells in real time within living organisms, revealing the intricate neural pathways and biochemical cascades that trigger and control bioluminescent displays. Understanding how specific neurons fire to orchestrate a complex light show, or how molecular switches regulate the on/off state of photophores, will provide fundamental insights into the biological control of light. This granular understanding at the cellular and molecular level is crucial for fully decoding the grammar of bioluminescent communication. The development of non-invasive genetic sampling will also be a game changer. Imagine tiny autonomous drones capable of collecting environmental DNA from the water column, allowing scientists to identify the species present and even infer their bioluminescent capabilities without ever disturbing the organisms themselves. This will provide a broader ecological context for observed light displays, helping to link specific bioluminescent events to the species responsible and their community interactions. Beyond pure scientific understanding, the study of bioluminescence holds profound implications for biomimicry and technological innovation. Nature's cold light, with its near-perfect energy efficiency, offers a powerful inspiration for developing new, sustainable lighting technologies that consume minimal energy and produce no heat. Imagine light sources for our homes or cities that operate on principles derived from deep-sea bioluminescence, dramatically reducing our energy footprint. Furthermore, the molecular components of bioluminescence, luciferins and luciferases, are already being used in biomedical research, serving as powerful tools for tracking gene expression, detecting diseases, and developing new diagnostic assays. Future frontiers will undoubtedly expand these applications, harnessing the power of living light for human benefit in ways we are only just beginning to conceive. The decoding of bioluminescent law is not merely a scientific endeavor, it is a profound journey into the heart of life's adaptability and creativity. Each secret unveiled, each pattern deciphered, enriches our understanding of the intricate web of existence on our planet. It reminds us that even in the most extreme and seemingly desolate environments, life finds a way to thrive, to communicate, and to manifest its presence with breathtaking beauty. As we gently drift towards these future frontiers, allowing the promise of new discoveries to settle softly in our minds, we feel the quiet excitement of what lies ahead. The deep ocean continues to hold its luminous secrets, but the persistent, patient gaze of human curiosity, empowered by ever-advancing technology, is slowly, gently beginning to illuminate its hidden stories. Let these visions of future understanding guide your thoughts as you slowly sink into the tranquil quiet, embracing the peaceful certainty that knowledge, like light, will always find a way to emerge from the darkness. A luminous dream, As our quiet journey through the glowing abyss draws to a gentle close, having traversed the intricate chemistry, the diverse life, the known purposes, the baffling blinks, the scientific quest, the ancient origins and the frontiers of future discovery, we arrive at a profound contemplation, the deep's last secret. This is not a single tangible enigma to be solved, but rather the enduring mystery of life's boundless capacity for self-expression in the face of absolute darkness, a luminous dream woven into the very fabric of our planet. Imagine one final time that you are suspended in the deepest, calmest ocean, far beyond the reach of any external light. Around you, the vast, cold silence is punctuated only by the soft, rhythmic pulses of living light. These are not just flashes for hunting or defense, they are the quiet manifestations of existence itself, a continuous subtle declaration of life in a realm that would otherwise be utterly devoid of such visual affirmations. The deep's last secret is perhaps this inherent, beautiful and persistent desire of life to illuminate itself, not always for a clear, decipherable purpose, but sometimes simply to be light. The pervasive blue and green hues, the occasional enigmatic reds, the intricate patterns that ripple across gelatinous bodies, the steady glows from bacterial symbionts, each contributes to a collective living lightscape, an internal universe of radiance. For many deep-sea creatures, bioluminescence is not merely a tool. It is an intrinsic part of their identity, deeply integrated into their physiology and their very being. It is the visual signature of their presence, a quiet hum of energy, made visible, a constant reminder that life finds a way to flourish, even in the most extreme conditions. Consider the profound implications of this pervasive glow for the creatures themselves. In a world without external light, their internal radiance becomes their reality. Their perception of their surroundings, their interactions with fellow inhabitants, and their very sense of place within the immense ocean volume are all mediated by light that they or their neighbors produce. It is a world where every interaction is potentially illuminated by the participants themselves, creating a dynamic, ever-shifting visual environment born from within. The deep's last secret whispers of a sensory world, so fundamentally different from our own, a world where the act of seeing is intrinsically linked to the act of creating light. This enduring mystery also encompasses the profound evolutionary pressures that continue to shape bioluminescence. Even after billions of years and countless independent origins, life in the deep is still refining its luminous strategies. New species are constantly being discovered, each often exhibiting unique bioluminescent patterns or mechanisms. This ongoing evolution suggests that the game of light in the deep is far from over, that new forms of communication, predation, and defense are still emerging, continuously adapting to the subtle shifts and challenges of their environment. The deep's last secret is thus a living, breathing enigma, perpetually evolving and revealing new facets of its luminous nature. Moreover, the deep's last secret extends to the unseen connections that bioluminescence might facilitate. We have focused on direct communication and interaction. But what if the ambient bioluminescence, the collective background glow of countless organisms, plays a more subtle systemic role? Could it influence the overall mood of the deep, or provide a constant, low-level visual reference point for navigation? Could the collective flashes of vast numbers of organisms create a diffuse, energetic field that somehow influences the broader ecosystem, a kind of biological background radiation that subtly shapes the lives of all who dwell there? These are the larger, more philosophical questions that still hover in the darkness, inviting us to look beyond individual interactions and consider the holistic impact of living light. The very resilience of bioluminescence, its ability to persist and diversify across such vast stretches of time and in such challenging environments, speaks to a fundamental principle of life: the drive to overcome limitations. Confronted with absolute darkness, life did not succumb. It innovated, it adapted, and it learned to carry its own light. This is the ultimate message of the deep's luminous dream, that even in the most profound quiet, even in the most crushing darkness, there is an indomitable spark, a persistent glow that affirms existence and continues to whisper its untold stories. As we conclude our exploration of these glowing depths, let the profound quiet of the deep ocean settle deeply within your consciousness. Feel the gentle rhythmic ebb and flow of understanding as the images of luminous creatures with their baffling blinks and unspoken dialogues softly recede into the tranquil spaces of your mind. The deep's last secret, its luminous dream, is a perpetual invitation to wonder, a reminder that the universe, both within and beyond our planet, holds infinite mysteries waiting to gently unfold. And so, as we drift away from the profound quiet of the deep ocean, its luminous secrets gently fading from our immediate focus, we feel the slow, inevitable pull towards rest. Like the ocean's tides which ebb and flow with an ancient rhythm, our consciousness now recedes from the waking world, drawn into the deeper, more mysterious currents of sleep. The unknown functions of bioluminescence, those baffling blinks and unspoken dialogues, find a quiet parallel in the unfolding landscapes of our dreams, where hidden meanings shimmer just beneath the surface of awareness, waiting to be softly perceived. Allow your mind to surrender to this natural descent, much like the gentle fall of marine snow through the tranquil water column. Release any lingering thoughts, letting them dissolve into the soft, comforting darkness around you. May the deep's luminous mysteries softly illuminate the pathways of your slumber, guiding you to a peaceful, restorative rest. Sleep well, goodbye, and see you again.